Welcome to this explainer. Today, we're doing something really cool. We are going to demystify a foundational calculus concept by building a bridge between two entirely distinct mathematical worlds. We're looking at the triple product rule. But forget about just memorizing a string of random joyless variables. Instead, we're going to discover how the rigorous, formal world of multivariate calculus perfectly intertwines with the tangible, highly visual world of Euclidean geometry.
So let's kick things off with a question that really transforms how we see abstract equations. How do you actually visualize a complex derivative? When we look at a blackboard covered in limits and deltas, it's incredibly easy to get lost in the symbols and, frankly, experience a mild sense of dread, right? But what if I told you that one of the most intimidating formulas in calculus is actually just the blueprint of a simple growing box? Okay, to keep us on track, here's our roadmap for today. We'll start with the triple product rule, move into the geometry of calculus, then visualize the volume change, tackle the limit derivation, and finally wrap up with the algebraic justification. Let's jump right into section 1, the triple product rule, a three-dimensional problem. Now, before we even look at a single equation, we absolutely have to get a handle on our variables, u, v, and rho. In a standard calculus class, these are pretty much always treated as arbitrary functions of x that just exist to make your exam questions harder. But here, we're stepping into Euclidean geometry. We need to treat u, v, and rho as the literal, physical dimensions of a 3D object, its length, its width, and its depth. And crucially, they are dynamically changing over an independent variable x, kind of like time. If you check out these handwritten notes, you'll see right away how this rule is defined. Up top, we have the derivative with respect to x of u times v times rho. And right below it, the geometrical meaning is explicitly stated. It measures the instantaneous rate of change of the volume of a 3D object. So this isn't just an algebraic exercise on paper. It's the mathematical calculation of a physical object expanding in real time. This is exactly why mastering this dual perspective is a real game changer. It completely turns rote memorization into physical intuition. Moving right along to section 2, the geometry of calculus, or how we actually see the math. Take a look at this incredible sketch. It perfectly shows us that taking a derivative isn't just about shuffling symbols around. It's physically stretching the length, width, and height of our container. Look at the original inner box there, and then check out the outer dotted lines representing the new expanded box. The changes are labeled delta U, delta V, and delta rho. This is multivariable calculus literally represented as physical space. We have an initial state, and then an expanded state after a tiny step forward in our independent variable. So the absolutely crucial takeaway here is that every single mathematical term you see corresponds to a tangible addition of space in our growing box. When you calculate du dx, you aren't just finding an abstract slope on a 2D graph somewhere. In this geometric context, you are measuring the exact physical rate at which one specific wall of your 3D container is pushing outward. Okay, on to section 3, visualizing volume change by slicing the space. This illustration is brilliant because it highlights the jump from our original volume V0 to our new volume V1. Look closely at the arrows pointing from that central mass out to the newly formed edges. By visually breaking down the newly added space, which we call delta V, into distinct geometric slabs, we can actually see the derivative. The total change in volume isn't just some random blob of new space, right? It's the sum of 3 distinct new rectangular slabs attached to the faces of the original box. One for the change in depth, one for the width, and one for the length. Now we're going to cross the bridge from that visual intuition we just built, those physical 3D slabs we were looking at, right into the formal rigor of an algebraic proof. Visuals are amazing for understanding the concept, for sure, but to truly master the math, we have to prove that our intuition actually holds up under the strict rules of calculus. Mastering both sides is the secret to making this entire topic feel natural, rather than just feeling like a chore of memorization. That brings us to section 4, the limit derivation, where we formalize that intuition. We can totally conquer the denser limit math by just breaking the expansion down into these 3 logical steps. It's like we're mathematical detectives hunting for familiar patterns. Step 1, we define our total volume change, delta V. Step 2, we set up our rate by dividing that change by our independent variable step, delta x. And step 3, well, that's where the calculus magic happens. We apply the limit as delta x shrinks to 0, which locks in that instantaneous rate of change. Now, I know this handwritten limit expansion looks a bit intimidating at first glance. It's a massive fraction with functions of x plus h. But notice how cleverly the terms are grouped. By expanding over the limit and adding and subtracting values to factor them out, the messy algebra collapses beautifully. It isolates the individual derivatives and reveals the exact mathematical counterparts to those geometric slabs we were visualizing just a few moments earlier.
And this table perfectly aligns our two worlds. It lays out exactly how the algebraic expansion of delta V perfectly matches the three distinct physical directions our volume is expanding. Check out term 1, V times rho times du by dx. Algebraically, it's just a piece of the limit. But geometrically, V times rho is the exact physical area of a face of the box, and du by dx is how fast that face is pushing outward, stretching the length. The math completely, 100%, confirms the physical reality.
Finally, section 5, the algebraic justification. This is our final proof. You know, sometimes expanding limits from scratch is just doing things the hard way. Actually, we can confirm all of this using a really neat algebraic trick. By grouping two variables together, let's say rho and u, into a single bracket, we can just apply the standard two-variable product rule that we already know. Nesting that rule twice completely skips the massive limit expansion, yielding the exact same three-part result in just a few clean lines of algebra. Ultimately, this elegant formula you see here is the final destination for both our geometric journey and our algebraic derivation. Whether you arrive here by drawing 3D boxes and slicing up expanding volumes, or by rigorously crunching through limits and nested derivatives, the truth remains exactly the same. The real power here comes from seeing how seamlessly these two methods harmonize with each other.
So, to summarize everything we've unpacked today, mastering this explainer means realizing that the triple product rule isn't just some rote formula you have to memorize. It's this beautiful intersection of physical geometry and formal limits. It gives us a visualizable description of a 3D Euclidean object expanding while still being completely grounded in rigorous multivariate calculus. The fact that the geometry and the algebra perfectly confirm one another, that is exactly what makes higher level math so incredibly satisfying.
I'm going to leave you to ponder this final thought. If an equation as seemingly dry as a three-variable derivative holds the literal physical blueprint of an expanding 3D object, what other abstract algebraic rules might be hiding beautiful geometric secrets? Keep asking questions, keep visualizing the math, and I will see you in the next explainer.